Hello, this is Dr. Bricker here with some hints for homework number 8, which is over chapter 7. So 7 is similar to 6. Chapter 6 is circular motion, so objects going in a circle. Chapter 7 is rotational motion. It's objects rotating along their own axis. So not actually going in a circle, like sort of a solid object rotating around its axis. Like an old record on a record player, for example, like this problem. So let's take a look at this first one. A record rotates at 33 RPMs. We want to know the angular speed in radians per second. And part B, what is the period of motion? So let's take a look at this. Okay, so 33 RPMs, 33 revolutions per minute. So what does that actually represent? Well, this would be the frequency, just not in SI units. So this is the frequency. The frequency is how many revolutions per a certain amount of time. The SI unit is revolutions per second. Here we have revolutions per minute. So again, it's sort of like it is the frequency, it's just not in the correct units. So frequency 33 revolutions per minute. Again, not SI unit. So I'm going to think about it like this: 33 revolutions per minute, and then I know 1 minute is 60 seconds. And I can figure out the amount of revolutions per second. That's what the frequency is, the amount of revolutions per second. Okay, so whatever that turns out to be, I'll actually do it here. 33 divided by 60, something like 0.55 revolutions per second. Now if you notice, they're asking for the angular speed. So omega is 2 pi times the frequency. So let's see how this works out. So 2 pi times 0.55 revolutions per second. The way you can think about this is it's 2 pi radians if you go around 1 revolution. Usually we don't really write the radians, it's more of a label than a unit. But if you want to, you can think about this as 2 pi radians per revolution, and then this answer comes out in radians per second. So I'll leave that part to you to finish the math on that. Part B says, what is the period? So the period is 1 over the frequency. So once you get the frequency in revolutions per second, 1 over that tells you the amount of time to go around for 1 revolution. And again, that is the period. All right, let's look at the next one. Okay, so 7.6, we have 2 children are playing tetherball, in which a ball at the end of a cord spins around a pole. After a really good hit, the ball makes 3 complete revolutions, so it goes around 3 times in 2 seconds. And we want to know the angular speed of the ball. So a hint here is, angular speed, it's actually listed here, the units, radians per second. So radians per second tells you that's the angular speed. Okay, so let's take a look at this. Okay, so we need this to be in radians per second. Right now we have 3 revolutions in 2 seconds. So we know 1 revolution is 2 pi radians. So if you just take a look at the units here, we have revolutions, we've got seconds, radians per revolution. The answer is going to come out in radians per second, which is what we want. So basically what we're doing, this would be 1.5 revolutions per second. That would be the frequency. We're multiplying it by 2 pi to give us the amount of radians per second. So I'll leave that part to you. So just be careful when you see revolutions per second. That's the frequency f. That's the amount of revolutions per second. When they ask you about omega, that's the amount of radians per second. So they're related to each other this way. 2 pi times f. Okay, good. Let's look at the next one. Okay, so 7.13, to throw the discus, a thrower holds it with a fully outstretched arm. Starting from rest, he begins to turn with a constant angular acceleration, releasing the discus after completing 1 revolution. The diameter of the circle in which the discus moves is 1.6 meters. Okay, so it must be 0.8 for the radius then. If the thrower takes 0.9 seconds to complete one revolution, starting from rest, what will his speed be what will the speed of the discus be at release? And then, as a reminder, you can always, to see the section that comes from the book, just hit review here. But let's take a look at this. Okay, so here's the kind of picture I've drawn. The discus is going to go around in a circle at the end of the person's arm. It takes 0.9 seconds to do one revolution, and they tell you starting from rest what's the final angular speed. Now it's tempting to just say, all right, one revolution is 2 pi in 0.9 seconds. That will give you the average angular velocity. That's not what they're asking for, though. You could get that if you want to. The average would be 2 pi radians in 0.9 seconds. And that would give you the average. But that's not the final. You start from rest, omega versus t. You start from rest, you get up to the final amount. This is the final amount, starting from rest. But if you just take 2 pi divided by 0.9, that would give you the average. So that's half of the final, right? The average would be half of the final. So you can do it this way. Get the average, and then to get the final is just twice the average. Literally, the average is the final plus the initial divided by 2. So if the initial is 0, then the final has to be twice the average. Okay, so I'll leave it up to you to get the numbers, but that's the way to think about this. And this is linear, meaning constant angular acceleration. Okay, let's look at the next one. Okay, so the crankshaft in a race car goes from rest. Okay, so again, rest means initial frequency of 0 up to 3,300 RPMs. So again, what does this represent, RPMs? This is the frequency, just not in SI units. This is 3,300 revolutions per minute. We need 3,300 revolutions per second, and then we can call that the frequency. Not the angular speed or anything like that, the frequency F. And this happens in 3 seconds. We want to know what's the angular acceleration. Okay, so that's a new variable. We'll have to talk about that. And how many revolutions does it make while reaching 3,300 RPMs? Okay, let's take a look at this. Okay, so we're looking for the angular acceleration. That's what alpha is. So remember, this is radians per second squared. And starting from rest, we get up to 3,300 revolutions per minute. This takes 3 seconds. What is the angular acceleration? And then how many revolutions do we go through? So again, you have to ask yourself, well, what is this 3,300 revolutions per minute? That's the frequency, just not in the correct units. So let me figure out what the final angular velocity would be. So if I can put this into radians per second, that's what angular velocity is. So 1 revolution, 2 pi radians, and then 1 minute, 60 seconds. So multiply everything on the top together, so 3,300 times 2 times pi, divide by everything on the bottom, which is just 60. That will give us the angular velocity. So the revolutions cancel out, the minutes cancel out, and then we're just left with radians per second. Okay, so that's only part of the problem here. We need to figure this out. And then we've got all of our rotational kinematics equations. So for example, we've got this one, omega final is equal to omega initial plus alpha times t. This is just like what we did before with final velocity was equal to initial velocity plus at. This is omega final is equal to omega initial plus alpha times t. So hopefully that rings a little bit of a bell. The initial is 0 here, so we've got to figure out we can get alpha from this equation. This is the first rotational kinematics equation. So if that's 0, omega final divided by t will give you alpha. Okay, and then part B is how many revolutions do we go through? So here's another couple of rotational kinematics equations. Omega final squared is omega initial squared plus 2 alpha delta theta. So instead of delta x, now we have delta theta, and it's going to come out in radians. We also have this one, which I don't think we'll need for this equation, but for this problem. But let's take a look. Delta theta, initial angular velocity times time, plus 1/2 alpha t squared. What I want to do is figure out the amount of radians I go through, and then I can figure out how many revolutions that corresponds to. So let's see which one will work for us. I want to figure out delta theta. It's tempting to use this one. This would actually work for us. You can get delta theta from this equation. The initial angular velocity is 0, and then 1/2 alpha t squared. So alpha we just got from the first part. The time is given in the problem. So you can get delta theta from this equation. Or we just figured out the final. The initial was 0. We know alpha because we just figured that out as well. So you could use either of these to figure out how many radians you go through. And then to get how many revolutions, remember 2 pi radians is 1 revolution. Okay, so again, when you get delta theta here, it will be in radians, and then use this conversion factor to figure out how many revolutions that corresponds to. Okay, let's look at the next one. Okay, in this problem, we've got these balls are attached to light rods and can move in horizontal circles. So we're basically looking down on these. And we want to rank from smallest to largest the torques. So remember what torque is. It's related to the force, but where is the force actually applied? So it's the distance to the pivot point multiplied by the perpendicular part of the force. So you've got to go through and see which one has the biggest torque. So this is F applied at R, so the torque would be F times R. This one is 2F applied at R. So this torque for the second one is twice as big as the torque from the first one. Now the third one over here, we've got a nice long lever arm, 2R, but the force is F. So the torque would be F times 2R. And this one over here, it's really big lever arm, relatively speaking, 2F. So this would be 2R times 2F. So then you can figure out which is the biggest torque. So again, torque, distance to the pivot point, and then the perpendicular part of the force. And in all of these, the force is perpendicular to the lever arm. Okay, and then you can move them over here, rank them from smallest to largest. Let's click to the next one. Okay, so in this problem, what is the net torque about the axis? So when you look at this picture over here, there's 20 Newton force applied at 4 centimeters, making it go counterclockwise. That's technically the negative direction. The positive direction. And so counterclockwise, positive direction. Clockwise, negative direction. And then you've got 30 newtons over here, also at 4 centimeters from the pivot point. So if you think about it, it's going to rotate clockwise. The net torque over here is going to have to be negative. Let's actually work it out and see what we get. Okay, so if you look closely at the picture, the radius is actually 2 centimeters because they're giving you the diameter is 4 centimeters. So the radius here is 0.02 meters. Okay, so we've got 20 newtons here. Here's the distance to the pivot point, 0.02 meters. That would make it rotate counterclockwise, the positive direction. And then over here, 30 newtons. Here's the perpendicular distance, also 0.02 meters. So the net torque, so this is tau, net torque, 20 newtons. Here's the distance to the pivot point, positive direction, minus 30 newtons, perpendicular distance, same thing, 0.02 meters. Put it all together, you get negative 0.2 Newton times meters. So a Newton meter is the unit of torque. Okay, let's look at the next one. Okay, so let's see. In figure 1 over here, force 2 acts half as far away. Okay, so it's over here. acts half as far from the pivot point as F1. Okay, so here's the pivot point. You've got F2 over here, half the distance away, and you've got F1 over here, which is 20 newtons. What magnitude of F2 causes the net torque on the rod to be 0? So net torque means it's not going to rotate. So if you've got 20 newtons applied at 45-degree angle, what does F2 have to be? And it matters where the forces are applied when you're talking about torques. Okay, so this is a certain distance away. This is half as much away. Okay, so we want to figure out what does F2 have to be so this thing remains stationary. Let's take a look at it. Okay, so here's the picture I have, and it's really important to have a nice picture when you're dealing with torques because it matters where the force is applied. Okay, so the torque from F2 is equal to the torque from F1. Now the torque from F2, and they don't give you these distances, we just know that this distance is twice as much as this distance. So you can call this like R2 if you want to. This one is R1. Okay, so R2 is half as much as R1. So I can do it like this. This would be F2 times R2. That's the torque because of this force, right? This is going to be equal to F1 perpendicular. So if this is F1, this is F1 perpendicular. It's the perpendicular force, part of the force, times the lever arm that we need. So they give us F1, we really need F1 perpendicular. So I'll leave it to you to get that. F1 is 20 newtons. You'll have to figure out how much F1 perpendicular is. And then we've got to multiply it by R1. Okay? But we don't know R1 and R2. We just know that R1 divided by 2 gives you R2. So let me just plug that bit of information in. So F2, and now we know R2 is R1 over 2, right? I'm just putting that in. If you take R1 divided by 2, you get R2. That's how I know this relationship. So then that would give us F1 perpendicular times R1. And then you'll see that the R1s actually cancel out. So you don't really need to know how much they are. You just know one is twice as long as the other. So that works out like that. Those would actually cancel out. Okay, so again, you'll have to figure out the perpendicular part of F1 and then use this bit of information to solve it. Okay, let's look at the next one. Okay, so let me just say a few words about this one. And if you notice, there's video tutor solution here. So check this out. Hold your outstretched arm so that it is horizontal. Estimate the mass of your arm. So you'll have to estimate the mass of your arm. And the position of the center of gravity of your arm. So if you think about your arm, it's there's more mass towards your shoulder, less mass towards your fingertips. So the center of gravity is not right in the center. It's probably, closer to your shoulder. And then you want to figure out the gravitational torque. So if you hold your arm out for a while, you'll start to feel that it's getting heavier and heavier. It's because there's a torque on the center of gravity of your arm that's pulling it down. The force here is provided by the force of gravity. So if you estimate the distance from your shoulder to the center of gravity of your arm, so whatever you think that might be, multiply it by the weight of your arm. So how do you get the weight of your arm? Well, it's the mass of your arm times g. So put that all together and you'll get the correct order of magnitude. By order of magnitude, I mean this could be written as 1 times 10 to the 0. This is 1.5 times 10 to the 1. 1.5 times 10 to the 2. So you probably won't get this exact answer, but you'll get something that has the same order of magnitude. Okay, again, check out the video tutor solution, but that's the way to do this. Force of gravity, which is mass times g, times the distance from your shoulder to where you estimate the center of gravity to be. So keep everything in kilograms and meters. Okay, let's look at the next one here. An athlete at the gym holds a 4 kilogram steel ball in his hand. His arm is 70 centimeters long and has a mass of 4 kilograms. And again, you can follow the steps on the video tutor solution here. What is the magnitude of the torque about his shoulder if he holds his arm straight out to the side, parallel to the floor? And then part B here, what is the magnitude of the torque about his shoulder if he holds his arm 55 degrees below the horizontal? Okay, so we're going to have to, in the previous problem, we can kind of come up with where the center of gravity is. It's not in the center. For this one, we're going to have to assume that the center of gravity is right in the center. It might not be the best assumption, but that's what we have to work with on this problem. All right, let's draw it out and take a look at it. Okay, so here's the picture I have. I'm just representing the arm as a uniform shape, even though that's probably not completely, it's definitely not completely accurate, but that's how I'm going to have to solve this one, just assuming it's got a uniform shape. So here's the steel ball in the hand. Here's the mass of the arm on its own. So even if you weren't holding a steel ball in your hand, if you put your arm out to the side, you definitely feel something, and really you're holding up the weight of your arm. So this arm on its own has a torque. The mass of the ball, the weight of the ball I should say, has a torque. This distance is L over 2. We're just assuming it's a uniform shape, so it's right in the center. This distance is L, and we just want to get the magnitude of the torque. So the net torque here would be the weight of the arm, this is just the magnitude, times L over 2 plus the weight of the ball, and the distance from this force to the pivot point, which is L. Okay, so here's the information I have over here. Mass of the ball, you might have different numbers for these, by the way. Mass of the arm, and then here's the lever arm, 0.7. So we're assuming that this center of gravity of the arm is at 0.35, right in the center. So this will just give you the magnitude of the torque. Okay, so put that all together. Part B is a little trickier, but not too bad. You'll just have to do a little bit of trig for this one. So this is 55 degrees below the horizontal. You still have the mass of the arm here, sorry, the weight of the arm here, the weight of the ball here. So weight of the ball, weight of the arm. What you'll have to do though is figure out the new lever arms. So this is like the distance to the where the weight of the arm is working. This is the distance to where the weight of the ball is working. Okay, so the way to do that is just with a little bit of trig. This is 55 degrees. You know that this distance is 0.35. This is 55 degrees. So you can figure out this this different dimension here. I was talking about it here, but it's the same thing as here. Same thing over here. You know that this is 0.35, or sorry, this is 0.7, this whole thing. If this is 55 degrees, you could figure out this distance. Okay, so it's the same idea, you'll just have different distances to the pivot point for part B. Okay, excellent. Let's look at the next problem. Okay, 7.48. The lightweight wheel of a road bike has a moment of inertia. Okay, they give you the moment of inertia here. 0.097 kilograms per square meter. Sometimes you have to solve for it, depending on the shape and the mass and the size. Here they're just giving you the moment of inertia. A mechanic checking the alignment of the wheel gives it a quick spin. It completes 5 revolutions in 2 seconds. Okay, to bring the wheel to rest, the mechanic gently applies the disc brakes, which squeeze pads against the metal disc connected to the wheel. The pads touch the disc 7.1 centimeters from the axis, and the wheel slows to a stop in 1.3 seconds. Okay, so there's a lot of information here. Let me read it one more time. Wheel, moment of inertia given, 0.097. A mechanic checking the alignment gives it a quick spin. It goes 5 revolutions in 2 seconds. So we could figure out the angular velocity of that, and we'll just assume that's what we're beginning with. So 5 revolutions in 2 seconds. That would be 2.5 revolutions in 1 second. You'll have to figure out how many radians per second that is. To bring the wheel to rest, the mechanic gently applies the disc brakes, which squeeze pads against the metal disc connected to the wheel. The pads touch the disc 7.1 centimeters from the axis. Okay, and really it's friction that's going to be slowing this down. The wheel slowed this down in 1.3 seconds. What is the magnitude of the frictional force? So be careful, they're asking for the frictional force, not the frequency. It can be really confusing. It's the same lowercase f here, but this is the frictional force. Alright, let's take a look at this. Okay, so here's a wheel that's spinning. You apply the brakes a certain distance from the center. They're disc brakes, so I don't think they're right here on the edge. I think they're, somewhere wherever that pad part is. And they tell us 0.071 meters. So what actually stops this? If something is spinning and rotating on its own axis, there has to be a net torque to stop this. And in this problem, the torque is provided by the frictional force. So here's a force, here's a distance, that's what a torque is. So the torque in this problem is because of friction. Okay, we haven't seen this yet, but the net torque, just like the net force was ma, the net torque is I times alpha. And then you have to ask yourself, what's actually applying this torque? Where's this torque coming from? That's what you have to supply here. And it's the torque because of the frictional force. So R times F. Okay? So this is Newton's second law for rotation. Torque is I times alpha. Where's the torque coming from? Well, it's coming from the frictional force. Not only is it the force, but where is it applied? So just by analogy, F is equal to ma. You don't need that for this problem, I'm just showing you. Net force is m times a. In the rotational world, the net torque is I times alpha. And then just like we did before with Newton's second law, you had to supply the information in this box. Same thing in the rotational world. Okay, and we're trying to figure out this frictional force. So we know where it's applied, so we know R, we know I. That's given in the problem. I is the moment of inertia. So somehow we've got to come up with the angular acceleration, which it turns out we can do. 5 rotations in 2 seconds. If I multiply this by 2 pi, because it's 2 pi radians for 1 rotation, this is the initial angular velocity. And then you start off with whatever this turns out to be. I'll leave it to you to get that. You go from this many radians per second down to no radians per second in a certain amount of time. They give you that in the problem. I didn't write it down here. You can get the angular acceleration. Omega final minus omega initial divided by time. Not the 2 seconds. This was just to tell you how much it was going to begin with. So you can get angular acceleration from however much time it took for it to slow down. And then once you have alpha, then you can go back to this equation. So I times alpha divided by R, that will give you the frictional force. I is given in the problem, R is given in the problem. You'll have to solve for alpha from this information, and then you can get the frictional force. Lots going on, but you have all the information to solve it. All right, let's look at the next one. Okay, in this one we've got a 250 gram, 25 centimeter diameter plastic disc spun on an axis through its center by an electric motor. What torque must be applied to have it go from 0 to 1500 in 4.8 seconds? Okay, so this information here, the 0 to 1500 in 4.8 seconds, you can get the angular acceleration from that, right? From 0 to 1500 RPMs. Be really careful with the units. 1500 RPM is perfectly good, but you need to put that in the radians per second. So from 0 radians per second to whatever radians per second you figure out from the 1500 here, in 4.8 seconds, you can get alpha from omega final minus omega initial divided by 4.8. That will give you alpha. What are we going to do with this information over here? Let's actually take a look at that. Okay, so torque is I times alpha. Like I said earlier, you can get alpha from the initial stuff that they give you, rotational kinematics equation. So to get the net torque, we've got to figure out what I is. So I is the moment of inertia. So for this shape, a solid disk, that's what I'm assuming this is, a solid disk, there's a table of formulas for the different moments of inertia. For this shape, if I look it up, it's 1/2 mr squared. Okay, so they actually give you the mass. They give you the diameter, but you can get the radius from that, half the diameter. And then once you know the mass and the radius, then you can calculate the moment of inertia. So the rotational world is just always one more step than the linear world. Back in the good old days, all you needed to know was the mass. Now you need to know the mass, but what kind of shape do you have? How big is the shape? So the role of mass is played by rotational inertia. Okay, so from the initial stuff they give you, you can solve for alpha. From the shape and the dimensions here, you can get rotational inertia and put it together to get the net torque. Okay, all right, let's look at the last problem. Okay, so a frictionless pulley can be modeled as a 0.9 kilogram solid cylinder of radius 0.36 meters, and it has a rope over it as shown in the picture. Okay, so here's 12 newtons applied over here at 0.36 meters, right? That's the, you can figure out the torque. 12 newtons, this would be 0.36 meters, so you can figure out the torque. There's 10 newtons here, also applied here on the edge, so you know the radius here is also 0.36 meters. These tensions are 12 and 10. What is the angular acceleration of the pulley? So in some ways this is kind of putting the whole chapter together in this last final problem. Let's take a look at it. Okay, so here's the picture I have, here's the information I have, and I also know the shape is a solid cylinder, so I can calculate the rotational inertia. 1/2 mr squared, just like we've saw before. So torque is I times alpha. Okay, so okay, excellent. So here's I can solve for that. We're trying to figure out alpha here. We have to figure out the net torque to be able to do that. So we're looking for alpha. We'll have to do some work, but we can get that. How much is the net torque? Well, the net torque would be 12 newtons where it's applied, R, that would make it rotate counterclockwise, minus 10 newtons. And I'm subtracting it because it's making it go the other direction. So technically, again, this is the positive direction, counterclockwise. So 12 newtons times R minus 10 newton times R. And R is given in the problem. So you actually do know the net torque. You'll have to calculate it. This is the net torque. So then you do know the torque. So alpha turns out to be this part here, 12 newtons times R minus 10 newtons times R divided by I. Excellent. So in this problem, you actually have to figure out the net torque from the individual torques. And then once you do that, Newton's second law for rotation still works, and you can solve for alpha. Okay, if you have any questions, just send me an email, and I will talk to you soon. Bye-bye.